Today is a very important day because today is the day that you officially become chemists. Because today is the day that we start approaching problems like this, stoichiometry type things, from the same angle that experimental research has to be done. Right? Do you remember back in chapter 8 when we did balanced equations and limiting reactant and things like that? I told you that the only way to relate multiple materials through the course of the reaction was through a balanced equation. Do you remember that? Okay, that was a lie. There is another way. Equivalent weights is the other way. And we're going to look at how to do this. All right. Point being, there had to be a different way. Otherwise, how did they figure out those balanced equations in the first place? There had to be another system to where they could do those kinds of relationships and develop the balanced equation. Right? It's a little awkward. It takes some getting used to. But you do already know enough chemistry to work this problem. But we've got to rearrange and massage around the things that you know to where you can piece them together in this kind of format. Right? You know enough of the chemistry to do it, but the approach is very unfamiliar compared to what we've done before. Right? So by the end of class, hopefully you will be able to work this one. The first thing you've got to get used to is it never looks like you have enough information. You're not given a whole lot of information there in the problem, are you? But between what is given there and what you know about the periodic table, then you do know plenty. And we're going to be using that to piece this together. Now, we are not going to do this one first, all right? We're going to work our way up to it. We're going to go back. We're going to define equivalence. We're going to define equivalent weights. We'll work some simpler problems. But before we're done, we'll be back to this one. And hopefully, you'll be able to work through it then. First of all, defining equivalence. Let's say this is our beaker. And in our beaker, we've got 4 chloride ions. You know that you can never have a beaker full of positives or a beaker full of negatives, because where you've got one, you've got the other, correct? Ionic charge is balancing out. If there's 4 chloride ions in there, and just for pretend, let's say that we had sodium ions there present to charge balance those, how many sodium ions would it take to charge balance all of those? 4. But what if we were using magnesium instead of sodium? How many would it take? 2. And if we were using titanium 4, it'd be 1. All right. 4 sodium ions, or 2 magnesium ions, or 1 titanium ion would do the same amount of work, correct? Because ultimately what matters is we need to have 4 units of positive charge in that solution to counteract all the chlorides, right? It doesn't really matter where we get our 4 units of charge. And so this is where the term equivalence comes from. Equivalent means does the same amount of work, or does the same amount of bonding. So 1 titanium ion is chemically equivalent to 2 magnesium ions, or chemically equivalent to 4 sodium ions. What we did before was a mole-based system. This is a charge-based system. Equivalence is a charge-based type of calculation. How many potassium ions would be chemically equivalent to 1 magnesium? 2. Apparently 2, because that's 2 units of charge, correct? All right. That's what you need to keep in mind as we go through all these formulas, is that everything is based on the charge of the particle. Moles tells you how much is present. Equivalence tells you how much work it can do. Based on charge, do you see that this 1 titanium ion can do 4 times as much bonding as that 1 sodium could? Yes, because of its magnitude 4 charge. All right, good. So at the bottom of the page, you have your definition for equivalence. equivalence can be calculated from moles by multiplying by absolute value of oxidation number or charge, whichever way you want to think about it. So 1 mole of sodium would be how many equivalents? 1. Because the charge here is 1, correct? But 1 mole of magnesium would be how many equivalents? 2. And our 1 mole of titanium-4 would be 4 equivalents. Okay. So what we're doing, instead of looking at things in terms of moles, we're looking at things in terms of how much work they can do, how much bonding they can do. We're incorporating that magnitude of charge into the mathematics. Question about that, about our definition of equivalence. Equivalent weight.
I have a question.
Yes.
Were you chemically equivalent in moles? What should we put in? Did you already talk about that in the basics?
We're chemically equivalent?
Yeah.
Does the same amount of work. Doing the same amount of work or doing the same amount of bonding. Equivalent weight is taking that same relationship that we've talked about over there, but trying to put it on a gram basis. Because when you go in the lab, you don't measure things in terms of moles or equivalents, you have to weigh them, correct? And so you need to be able to relate equivalents to grams just like you would moles to grams. And so the definition here, equivalent weight is calculated by dividing molar mass by absolute value of the charge or oxidation number. So for something like sodium, where this is the molar mass, what's the charge of sodium? 1. That 1, that denominator, is coming from this relationship here, where we're saying that there's 1 equivalent per mole. 1 mole is 1 equivalent for sodium because its charge is just a 1. Mole units cancel, you have your answer in grams per equivalent. Magnesium has a molar mass of 24.305, and that's 2 equivalents per mole. 1 mole of magnesium is 2 equivalents, right? We still got that on the board over there. Because of its higher charge, 1 mole would be 2 equivalents. 1 mole of magnesium weighs this much and carries this much charge. Think of it that way. For 1 mole of magnesium, this is its weight and this is its charge. And so if you divide that out, that comes up to be 12.152, I guess, grams per equivalent. Compare this equivalent weight to this equivalent weight. Those are equivalent weights, meaning if you had a reaction that required 22.98977 grams of sodium to get it to completion, if you used magnesium instead of sodium, then this is how much it would take. 12 grams of magnesium does the same amount of work as essentially 23 grams of sodium. Those weights do equal amount of work. We're shifting what we talked about over there on a particle basis to now on a gram basis. Aluminum, 0.9938 grams per equivalent. This is the equivalent weight for aluminum. Rounding these off, 9 grams, 12 grams, 23 grams. Basically, 9 grams of aluminum would do the same amount of work as 12 grams magnesium or 23 grams sodium. Question about that? Those are equivalent weights. Those weights would perform the same amount of work. Now, the absolute value thing just means that it applies to negatives as well. If you're dealing with sulfide, for example, 32.066 is its molar mass. Has a charge of -2, so that's 2 equivalents. 16.033 grams of sulfur. That's its equivalent weight. First of all, is there a question about how to get equivalent weight? All right. How many grams of aluminum would 16 grams sulfur react with? Apparently 9, right? This 16 grams will react with how many grams magnesium? 12. Or 23 grams sodium, right? Those are all equivalent. Things react in different proportions based on their charge, and if you factor out the difference of charge, then everybody's on a one-to-one basis. So these are all equivalent in terms of their ability to react.
And what about diatomic elements?
That's one of the really nice things about equivalent weight, is it doesn't matter if they're diatomic or not. Because like if you're doing oxygen, and for this one I'm just going to lop things off to whole numbers to make it easier. But if you're doing elemental oxygen, 1 oxygen, then that would weigh 16, but carry 2 units of charge, right? And so that would be an equivalent weight of 8 grams per equivalent. But if you treat it as diatomic, then it weighs 32, correct? But when it reacts, it would give you 2 of these ions, and now the charge is 4, and that's still 8 grams per equivalent. So you don't even have to keep track of who's diatomic in this system. The safest way to do it is just take it straight off the periodic table. Right? Some people prefer to stick with diatomic, but I've seen this so many times where they'll double the weight for it being diatomic, but they forget to double the charge, and then you're messed up. Right? So it's safer, not better, but less error prone if you just take the information straight off the chart and not think about diatomic or not. Question about that one, about oxygen, or any of your diatomic ones. The one thing you do have to be careful about is things like iron. Because iron can have multiple charges. If you're talking about iron 2, then this is its molar mass, and this is its charge. But sometimes iron is a +3. And so 3 is its charge, right? Those are not going to have the same equivalent weight because they're not reacting to the same degree. I'm just going to round these off to whole numbers. Not that you should ever really do that, but compare those two.
Is that what you'll have us doing the test, or you want us to round it?
No, I do not want you to round. Keep with them like over there. It's just kind of easier to look at the numbers for the moment this way. If we do round, this comes up to be at 19 grams per equivalent, whereas iron 2 is 28 grams per equivalent. So if you had a reaction that required 28 grams of iron 2, you could do it with 19 grams of iron 3. Those are equivalent. And that reacts with 16 grams sulfur, 8 grams oxygen, 23 grams sodium, et cetera, et cetera, et cetera. Those are all equivalent. Question about that? All right. when you're dealing with a compound. Oh, that didn't print very well, did it? It's still the same definition, but what you have to look at with a compound if you look at each of these three compounds, they all have no net charge, correct? But you're not going to divide by 0. First of all, mathematically, that would give you problems. And second, physically, that wouldn't really be accurate anyhow. Because even though these are neutral compounds, they don't remain intact when you react them. The positive and the negative go different ways, and they react with different things. And so what you look at here is the charge within the compound. And we'll practice these ones down here along with these. And I'm not going to take the time to figure out what their molar mass is, because you can do that from the periodic table. The thing we've got to emphasize is the charge. When HCl reacts, you get a positive 1 and a negative 1, so your charge here is 1. That compound is balanced at a magnitude of 1. The charge inside of magnesium sulfide, these are balanced at a magnitude of 2, so it would be molar mass divided by 2. What's the charge in sodium phosphate? What's the charge of sodium? 1, but you got 3 of them, correct? Phosphate's a negative ion. It's a negative 3, actually. So what is the charge balanced at? 3. Therefore, molar mass divided by 3 would be its equivalent weight. For aluminum oxide, formula weight or molar mass, we're going to divide that by what number? Well, it depends. What's aluminum's charge? And you got 2 of them. So 6. If you don't remember that, you should still should be able to figure that out based on oxygen, because oxygen forms a negative 2, right? And so either way, that's still a magnitude 6, correct? Whether you look at it in terms of positive or negative really doesn't matter. Either way, that's a magnitude 6. So for aluminum oxide, equivalent weight equals molar mass divided by 6. TiS2, what do you divide by there? 4. Titanium can have a couple different charges, but sulfur's a negative 2, right? So 2 of them is negative 4. That should be a capital B. This is uranium 6 bromide. Charge 6. And aluminum phosphate. Charge 3. Okay, 3. You total up the weight, that'd be your molar mass, and you divide that by 3 to get the equivalent weight. Question? All right, that's your definitions.
How about in there? In the sodium, we had 3 positives, and because the P is negative 3, what about the oxygen?
This phosphate is a polyatomic ion, and that whole thing is negative 3. Okay, we were not looking at it in terms of atoms, we were looking at it in terms of ions. And that phosphate is polyatomic. Problem 19, do the nitrogen part right now. See what you get. Just do the nitrogen part. periodic table says a mole of nitrogen is 14.0067 grams. Periodic table also says nitrogen charge is -3, right? So putting those two together, that gives you the equivalent weight. All right, good. Problem 20, we'll do a couple of these. If we're dealing with 404.7 grams of strontium, and we want to know what that is in units of equivalence. Our definition of equivalent weight is molar mass over charge. Now I'm going to work this out two different ways, okay? So leave room that you can write this down, because you'll see one way that you prefer more than the other. It really, one is just a more condensed form than the other. If we go strictly by the definition of equivalent weight over there, then we would put the grams of strontium and the charge of strontium to calculate that equivalent weight. According to the periodic table, a mole of strontium is 87.62 grams and carries how much charge? 2. Because it's in group 2, right along with calcium and magnesium. Those are exclusively +2s, right? All right, now up above, I'm going to work it a second time. Once you're comfortable with equivalent weight, you'll be comfortable putting it in together like that. Or you may prefer this. We've got our grams, 87.62 grams of strontium is 1 mole. That's just plain old molar mass, like we've done before. And then 1 mole of strontium is 2 equivalents. That was our first definition of equivalence up here. Because its charge is 2, 1 mole of strontium would be 2 equivalents. And that's the same calculation. It's even the same conversions. It's just that one is written in 2 parts and the other is more condensed. Grams to moles, moles to equivalents, or if you're comfortable with your definition of equivalent weight, going straight from grams to equivalents. Everything that's in this term is based on 1 mole of the material. It's how much that 1 mole weighs and how much charge that 1 mole carries. 87.62 grams of strontium would carry 2 units of charge. Question, Doctor? Question?
You just calculate out the answer.
Yeah, and just do the math, yeah. But that's your setup for it. This lower one then, where it brings in molarity. Molarity is moles per liter, correct? So setting that one up, 44 milliliters of solution. Thousand milliliters being a liter. One liter containing 3.00 moles H3PO4. Nothing new so far. That's molarity like we did back in chapter 8. Milliliters to liters, liters to moles, and now we need to go moles to equivalents. What's the charge inside of H3PO4? is 3, magnitude of 3. So 1 mole H3PO4 would be 3 equivalents. And really, we're just dissecting that phosphoric acid. The hydrogens give us 3 units of positive charge. The phosphate is -3. That's a magnitude 3. So 1 mole is 3 equivalents. This is the new part. Question. All right. We're ready to move out of definitions and into an actual reaction calculation now. Problem 21.
Actually, could you explain the end part of that one again?
The charge part?
The new part, yeah.
That's just dissecting this in terms of what you've got in terms of positive and negative ions. You've got 3 hydrogens. What's hydrogen's charge? +1. But 3 of them collectively is +3, correct? That's all you need to know. Because it's a neutral compound, that means that the negative ion, even if this is not something you recognize, it has to be complementary to that or it wouldn't be neutral, right? And so that's why you can focus on either the positive or the negative and not have to deal with both. This is apparently balanced at a magnitude of 3, meaning 3 equivalents per mole. All right. So this is our first reaction-based one. What mass of sulfur could be reacted by 5 grams of aluminum? I'm going to work this out the mole method like we did in chapter 8, and then separately by equivalents. If we were going by moles, then the first thing you'd have to do is come up with a balanced equation. Symbol for aluminum is Al, symbol for sulfur is S. You got to ask yourself if one of those is diatomic, because that makes a difference in the mole method. Is either of those diatomic? No, neither one is. We're reacting aluminum with sulfur, and we're forming a product. We figure out what that product is based on their charges. What's the charge of sulfur? -2. Charge of aluminum? +3. So what's the compound? Al2S3. Because 2 aluminums gives you +6, 3 sulfides gives you -6. That would be your product. And then we would balance the equation, which would require a 2 here and a 3 here, correct? And then after you've got all that done, then you can actually start on the math, which would look like this. 5 grams of aluminum, 26.98154 grams being a mole. Two moles of aluminum react with 3 moles of sulfur. And then molar mass of sulfur, 1 mole of sulfur is 32.066 grams. The common link in the equation is the mole ratio. They're reacting in a 3:2 ratio. We use molar mass to go in and out of moles. So there's nothing new in that part. That's the old method. That's the mole method. And you do the math and you get 8.91. But that's the process. Doing this same one by the equivalence method, we don't need the balanced equation. We can go straight into the math. Here's our 5 grams of aluminum. And plugging in everything we know about aluminum, 26.98154 grams of aluminum carries how much charge? This is your equivalent weight term. 1 mole of aluminum weighs that many grams and carries that much charge. All of that's straight off the chart. And then here's the key part. This is where we want to relate equivalence of aluminum to equivalence of sulfur. And a while ago, almost in passing, I said that things react differently based on differences in charge, and when you factor out differences in charge, you put everything on a one-to-one basis. It will always be a one-to-one ratio, meaning once you find the equivalence of anybody in that reaction, then you automatically know the equivalence of everybody in the reaction, because it will be the same number, because it will be a one-to-one, period. Absolute, always. Reactants, products, doesn't matter. Everybody is present in the same number of equivalents. They're reacting in the same number of equivalents. And then we need to go for sulfur, from equivalents back to grams. Periodic table says 32.066 grams is how many equivalents? 2. The charge, the column it's in tells you the charge it carries, correct? And then you do the math and you still get 8.91, because it is a different way of doing the same thing. Do you see how that works? Do you see how that's comparable? Do you see how even the mathematics is identical?